Okay, so welcome everybody. Also welcome to those of you watching online. I will be talking briefly and give you a few highlights of a project that has been going on for 2-3 years now, and we'll be talking about autism disorders and electronic health records. Before I tell you about that, I wanted to tell you I've been working in this field for a while, and one of the first projects we did, we were actually the first ones to build an app, and it wasn't called an app yet at that time, to teach kids with autism to communicate. So I talked to a lot of patients, to parents, to clinicians, and so the language was pretty familiar to me. So when I came to the University of Arizona, it was actually a smooth transition to finding collaborators here to continue in this field, but doing something very different. So we're not building any apps here. What we're trying to do is we're trying to help find an answer to the question, why is the prevalence of autism increasing? And it has been increasing for years. So currently, the estimate is that 1 in 59 children has autism. And we don't really know why. One of the reasons is because it's difficult to get large data sets because the children are so different. So that is one of the things we try to help with. Now, you may wonder, how do they know this? 1 in 59 children, right? So they do this by doing surveillance. So the CDC funds 11 states and a team in every state, and they go out, and so the Arizona team is at the University of Arizona. So this team goes out to a catchment area, in our case that's in Phoenix, and they collect electronic health records and school records from kids that are 4 and 8 years old. And then they review this. And so the first review, they read everything, and it takes an hour to 3 hours. If they see any signs of autism, they put this in the database. And then a clinician reviews it again, takes 30 minutes to an hour and a half. That clinician makes the case decision, autism or not. And this is where we come in. This takes several hours per child, right? And so in doing this for about 10 years, they've collected in Arizona about 5,000 records, which is a lot of work, but for most people in IS, this is a tiny data set. So we want to help improve that. We want to speed it up. Instead of a few hours, we want to go to half a minute, maybe a minute and a half. So that's our goal, so we can help them answer the question. So there are 2 tasks that we address here, in blue over there. The first task is the harder one. We want to get information out of the electronic health record that tells us which diagnostic criteria were identified in the child. The second task is easier. This is just looking at the entire record and tell me autism or not. So I'll tell you first about the first task. This is an example of what it looks like. On the left-hand side, we have our diagnostic rules. On the right-hand side, we have some examples of text that we have to match. So the entities that we have to extract, the text we have to match, it's very varied. They can be long, they can be short, they use a lot of different words. So it's a very tough task for us to do. And there are 12 of these rules that we want to recognize in the text. And to make it even worse, this is how we really started. So we get printed PDFs with handwritten codes on it. And that we had to turn into electronic health records. So we started with a tiny data set, because this we had to turn into an electronic version. And so because we started with a whopping 43 electronic health records that we coded, we use a rule-based approach, not a machine learning approach, to try and get these entities and match them in the text. What this means, a rule-based approach, is we eyeball the text, we read the text, and we try to come up with patterns that describe these diagnostic rules as they are expressed in the text. So really what we do is we create fancy regular expressions. That's what we do. And then when you do this long enough, and we did this for about 2 years, then you can actually get a really good system that is very precise. So one of our latest evaluations, we looked at some new records and we evaluated them, and we saw that we get about half of all the annotations we can get automatically. But we are very precise. So usually when we say this is criterion A1A, then we are correct. So that's a pretty good thing. It's so good, really, that the epidemiologists, they're already quite excited about it, because we could run this on their 5,000 records and give them some data they had never seen. So they could compare, in this case, the changes of the diagnostic criteria over the years for kids with autism and those with autism. So they're already excited. But being an IS, we always have this little voice in our head that says, we got to automate this, right? We cannot do rule-based, can't publish rule-based. So we try to automate it, because if we automate it, and we can do this by algorithm, even if we have to train it for 2 days, it's only 2 days. It's not 2 years, right? And we might even be able to switch domains. So we had a first approach, a machine learning approach. We went straight to deep learning, and we got actually quite good results. Overall, the numbers may look a little bit lower, but when you compare algorithms, you look at the F measure, and these are very comparable. So with the machine learning approach, what we find is we get some more of the annotations, but we're a little bit less precise. But this is a first try, really. So there are a lot of features that we can try, a lot of different combinations to get these numbers up. So we're on a good track. We can automate this. We're confident we can do better. So this is the first task, really. This was the hard task. The next task we're addressing is a little bit easier. This is where we say, this record, autism or not, right? So we try to assign case status. In this case, we start out with a brute force approach. Just give me the records, just give me the algorithms, and we'll play a little bit with the features that we give the algorithms. So this is an overview of one study where we played with 9 different types of features: frequent words, all words, less frequent words, different combinations. And so we compare how well this does. If we were to assign autism to our entire data set, which is no effort, we would be 51% correct. So that's the number we want to beat, of course, because we're going to make some effort here. This is a first set of results using very basic algorithms. So you can see we're about 80% correct, which is pretty good. We're very happy with these results, using standard machine learning algorithms. We did some deep learning, but I think for this particular one, the data set is way too small, because we dropped 10% in accuracy doing deep learning. But lots of things we can do. So one common thing many of you will know is we can combine these algorithms. So one of the things we can do is we can give each algorithm a vote and put them in an ensemble. So each algorithm is going to vote on the record, autism or not. And then we combine the votes and we test what we get. When we do that, we get about 2% more accuracy. Now, you might think 2% is nothing, right? But in information science and computer science, we all get very excited when we get 2% more accuracy. So for us, this is really good. This is a big improvement, just by doing these combinations. What we did next is something that, as far as I know, nobody has done. We looked at different ways of combining features. So we gave a certain set of features to an algorithm, let it decide, give a different set of features, let it decide, combine the votes, and look at what we get. Again, we get about a 2% improvement in accuracy. So completely different approach. Again, we're very happy with these results. So what we want to do is combine these and get our accuracy levels up, right? So there is this other part, though. We've been working for 2 years on that rule-based parser, remember? That's a lot of effort. So what if we use all that work and use the terms that we identified as important and use those as features for the algorithms? Okay, we can do that, but then we're back to manual, right? But we're going to do it anyway. So we check what we get. And when we tried that, we got really good results. But there is this little voice in my head saying again, you got to be automated. You cannot do manual. It's too time consuming. So we have this manual approach to creating important features, lexicons. We also tried and automated it. So instead of reading and writing down the terms, we said, let's just use everything that they underlined in the records. That's kind of automated. It's getting close. So we get everything. We get synonyms, we get hypernyms, we get related terms, and we group them. And let's use that and see what we get. And so we did that. And you can see on the left, manual lexicon means 2 years' worth of effort used by these classifiers. We get almost 85% accuracy now. So this human knowledge, this expert knowledge, gave us a higher accuracy. Can we automate that? Yes, we actually got 86, almost 87% accuracy on deciding if a case is autism or not. So what we want to do with this is at some point we want to combine these things into a classifier that goes up to maybe 90% or so. Because if we can automate it, once we get to 90%, we're probably just as good as any of the clinicians. And we can start playing a role in the decision process. We can check how we can incorporate this in the workflow. Can we do it automatically or semi-automatically? And maybe we can go from 3 hours per record to 30 seconds, which would be a big improvement. And ideally, we can do the entire United States or maybe the entire world and get a real large data set, combine it with other data sets, and then finally solve the prevalence question. That's where we want to get. And I should say, I take all the credit here because I'm standing here and I'm talking, but really this is the students' work. And one of them is sitting right in the middle in the back. That is Yang Gu. Yeah, wave. She did most of the work here. She's a doctoral student and also master's student and undergraduate students work on this project. Thank you.